So we now welcome Dr. Flavio Gili from the Fraunhofer Institute for Applied Optics and Precision Engineering from Jena. Thank you so much, Dr. Gili, for being with us. Great pleasure.
Yeah, thank you for the kind invitation and thank you for the presentation. I will now start sharing my screen. All right, so without further ado, now I would like to present you a little bit what is, well, the research that we are conducting here at Fraunhofer IOF regarding especially quantum technologies and trying to find application specifically for cancer diagnosis. So I'm really trying to make a high-end kind of a presentation in which I will try to explain you that and also convince you that to some extent quantum sensing can provide an added value for this kind of application. Maybe before starting, a couple of words about Fraunhofer IOF, where we come from. So in general, as you might note, is that we are a research institute, so no hospital or medical company. And so what we do here is that we specifically focus on precision engineering and optics to essentially bring systems from the very early design and simulation and manufacturing stage up to integration and finally get them ready for end usage and applications in various fields, as for example, for this case in the biomedical field. And in general, in Fraunhofer IOF, I come from a department which is the Photonic Quantum Systems department, where actually we are looking for enabling technology, which is photonics, and try to find applications for quantum systems on 4 different axes of application, which is communication, computing, imaging, and sensor and metrology. And with that being said, we'll now jump to my outline, in which today I will essentially give you a brief overview of what is quantum light and what is the added value that it can bring for all sorts of applications. Then I will move on explaining a little bit what is our implementation, which is microscopy based on quantum interference. And then I will also finally give you an outlook on how we plan to use this kind of system for cancer detection. So now for the first part, of course, the question you might ask you is, okay, what is the need for quantum light? Like, what is the added value that it can bring with respect to already developed and state-of-the-art classical systems? So in this sense, one can move along several directions, and the first, of course, would be resolution. So using quantum light to improve the resolution of your microscopy system. The second direction to go is, of course, try to investigate ways to improve the signal-to-noise ratio, meaning that one can essentially obtain the same information about your sample, or you can maybe detect cancer with a less amount of light, so thus saving time and also with less risk of damaging your sample. Very interesting is also the possibility to actually use detection at a spectral range that is different from the illumination range. So we already have listened to a talk dealing with mid-infrared and near-infrared diagnostics for cancer. So here in quantum sensing can also offer the possibility to actually perform illumination in the same range, so near to mid-infrared, and detection in the visible, where detectors are far more developed. And finally, as I already briefly talked about, the possibility to perform imaging and spectroscopy with low levels of light, meaning that essentially you have minimal, let's say, perturbation of the samples that you want to investigate. And this is actually mostly the 2 applications that we are looking for in our research. Then again, what is very important to state is also, at least from a fundamental or a high-level point of view, what is exactly that we are using in terms of quantum light. So we mainly use what are called the twin photons or photon pairs that are generated through a nonlinear process, a nonlinear optical process. But what is important here is that essentially when you shine a laser onto some very specific materials, you can actually get these twin photons. And what is nice about these twin photons is that they will share some properties, or in other words, they will exhibit quantum correlations. So the first important correlation that we want to exploit is the spectral correlation, meaning that if you measure one of the photon, then or the wavelength of one photon, then the wavelength of the other photon will be known. And this is especially important for the application I talked to you about before, where, for example, one can, for example, illuminate a sample in a specific wavelength range, like the near or mid-infrared, and detect, for example, in the visible. And the other thing is, of course, spatial momentum conservations that are then important to actually ensure imaging conditions. So then again, what we are really focusing on for our research, as I already stressed, is, well, again, trying to look for interesting processes and find applications in the mid and near infrared. Well, while on the other hand, we exploit the high technological level of detectors for the visible. So this now brings me to the second part of my presentation today, in which I will try to explain in easy words what is the concept of our interference-based mid-infrared microscopy. So the effect that we are looking into is called induced coherence without induced emission. And what happens in this effect is that if you consider an interferometer, so for example, a Mach-Zehnder interferometer, what happens is that you can insert some photon pair sources into these interferometers. And so then essentially you can have, as I said, the paths that are followed by the twin photons that you generate, so the quantum light that you generate. And you can have, for example, one object in the path followed by one specific photon. And then what happens is that when you do your magic really well, and so you align your interferometer really well, what happens is that you can actually transfer any information on this object that is placed on this photon path over here to its twin photon. So essentially, you can just infer information about this object by measuring photons that actually never directly interacted with this object, and this is called imaging with undetected light. And again, well, maybe the physical conditions are not so interesting for this audience, but what is important here is that, again, this object can be something that is relevant, for example, for the near and mid-infrared, and here you can actually detect in the visible, where your technology is very well developed. So this is, again, a very high-level kind of physical system, so of course it's a very complex system. And of course, you might imagine that it's actually quite difficult to scale it up. And so what we actually did in Fraunhofer, starting from 2021, is to try to bring down this very complicated interferometric system down to a compact version that can actually then be used for applications. So this is actually what we did here, where we essentially try to scale down this complicated kind of nonlinear Mach-Zehnder interferometer into a more compact version, which is more a Michelson-Morley geometry. And so this was, again, a result of 2021. And with this system, we could actually then, at least as a proof of principle, demonstrate video rate quantum imaging with the possibility even to perform some signal-to-noise ratio improvements by background rejections. And again, this was a very preliminary work. We even performed first a video or quantum video of some living objects. Then again, this of course is still very far from application. So I promised I will talk about cancer detection. So and this is actually what we were looking at starting from 2021, where we got these first results. And this now brings me to the last section of my presentation today, in which I will specifically talk about this latest project that we are working on, which is the Cancer project, in which we are looking into indeed demonstrating quantum microscopy with undetected light in the mid-infrared, and specifically in the fingerprint region, where one can really detect specific biomarkers for cancer, and hopefully provide some added value for especially our clinical partner, which is the Jena University Hospital. Before actually moving to the applications, one problem that we needed to solve so far was actually the resolution. So actually, the state of the art is full of works already that are already mainly dealing with the spectroscopy with this technique. So again, looking at the mid-infrared while detecting in the visible. The problem with microscopy is that actually in the wide field, at least, the resolution has certain problems that are bound to technical limitations within photon pair sources. So this is why we dedicated a lot of effort to actually trying to solve this problem. And the solution that we found was actually to implement a scanning approach for our mid-infrared quantum microscope. But eventually we managed to to implement this. So so far our first demonstration is now operating at 2.4 micron wavelength, but we are now planning with this cancer project to extend our operational regime up to 6 microns, where actually more sophisticated tests with our university hospital partner can be then performed. And actually, about the resolution improvement that I talked to you about, without going too much into details, what we demonstrated compared to state-of-the-art wide field approaches is that indeed we can get to a resolution of 16 microns so far, which is already starting to be then something that we can use for applications, at least in the near future. And of course, this can then be scaled up hopefully to the nanometer regime, where actually then we can really compete with state-of-the-art classical systems. So this brings me to the conclusion of my talk, but before concluding, I would of course like to acknowledge the group whose support was fundamental in the achievement of the results I presented you today, and of course funding agencies and you for the kind attention. And I'm happy to take any questions if you have any.
Thank you so much, Dr. Gili, for this inspiring presentation. Up to now, there are no questions in the Q&A session. So I have as a simple medical doctor, I have a simple question. So you mentioned the capability to retrieve an image with undetected light. Just to be very clear about the big picture, do you think that this possibility could revolutionize radiology or imaging, cancer detection, and some areas of radiology?
There is also, to some extent, some work going on in the X-ray regime, but this is so. In principle, I would say it is possible. So, of course, not in the next 5 years, not in the next 10 years. We are talking about very, very distant future, possibly. But I mean, I know that there are some works on this direction already.
But you are able to detect something that is up to now undetected.
Undetected here is a little bit different. So it refers to the possibility to let's say retrieve or reconstruct an image. So telling something, perform a diagnosis using photons that never interacted with your sample.
Interesting. Thank you so much. So Sarai, thank you so much for your question. What size are the devices and how realistic is it for use for us to expect a bedside device working with this interferometry technique?
So just to give you, yeah, it's a very good question. So just to give you an idea, maybe, yeah. So this is so far a system that we have. So, so to say, well, I don't know, half a meter maybe in length or something like that. What we are aiming for within the cancer project is to have a more compact version of this, ideally within a shoebox. Then again, of course, the other long-term development would be actually to go towards integrated optics. But this is something that we can foresee for the next 10 years or so.
Impressive. Thank you so much, Sarah, for your excellent question. Thank you so much, Dr. Gili. No
Thank
more
you.
questions at the Q&A section. Thank you again. It was a great pleasure to having you here.